Let's now move on by considering invariant preservation again. And specifically, I want to consider ML out. And if you can recall what we did earlier, we tried to prove that ML out was able to preserve invariant to 4. And to really do that, we have to introduce invariant condition number 5 about the two traffic lights not being green at the same time, right? So now we're considering another invariant, which is 2-3 rather than 2-4. So that's something I want to clarify right in the beginning. Otherwise, you might be confused about why are we revisiting the same proof sequence again. We are not. Again, we are talking about ML out events, but invariant condition we want to preserve, and we want to prove that it can preserve, is actually invariant to 3 as opposed to 4, which we did earlier. Symmetrically, we will also consider IL out invariant to 4 as opposed to 3, which we did earlier. So ultimately, we really want to consider the 4 proof obligations that are generated between the two events, ML out and IL out, and also the two invariant conditions, invariant to 3 and invariant to 4. We already considered 2 of them in the earlier part, and now we're going to consider the other 2, right? So it's really important for you to see this bigger picture without getting lost. Since we are assigning exercises to you throughout the lecture this week, you want to make sure where you are without getting lost. So this will be the complete sequence for this particular invariant preservation proof obligation. Okay, I'm going to go over some highlights of it, and then we'll do some discussion. Okay, let's take a look. And since now we are talking about ML out, so let me highlight it. So let's say ML out over here. And let me use maybe blue just to be consistent. We got ML out over here, so that's the events. And so the concrete guard will be MLTL equals green. So that's why you see in one of the hypotheses, it should be the concrete guard. And also, we got the before after predicate for A, which will be A prime equals A plus 1. So that's why you also see A plus 1 over here, right? So the derivation is something that we have done so many times. Maybe for this part over here, I'm going to skip it. If you got any trouble filling the gap about how to come up with this particular post-state version for invariant number 3, which is over here, where A was replaced by A plus 1. If you got any trouble with this, let me know. Otherwise, I'm going to assume you're okay. All right. So that's about the invariant preservation that we have to do. And as an exercise, I want you to try to specify the other one, IL out, and also invariant to 4 over here, right? And there's something I want to mention again. IL out, invariant to 4. Okay, don't really get confused. The one we did earlier was about IL out, invariance to 3, was already discussed earlier. You can definitely refer to the two different attempts that we actually did earlier, and then we figure out we should really add the invariant number 5 in order to discharge the proof sequence. Similarly, for this one over here, the earlier one that we did was about ML out. Invariance to 4 was discussed earlier. Alrighty, and let's now consider the proof for this one specifically. This one over here, this proof sequence over here. It turns out this proof sequence over here is unprovable. However, to really reach the stage where we know that it's unprovable is also very valuable, and you should really try to do the exercise as well. This is the complete proof all the way until this particular sequence, shockingly, that one cannot be really discharged. It cannot be proved. And we're going to do the similar deep analysis about this unprovable sequence to see what kind of hints it gave for us to really revise our model maybe further. That's something we'll see. Before I get to over here, I'll talk about it, but I'd like to just show to you the steps. We're going to apply monotonicity, we're going to apply implication R, and also implication R twice, right? For these two, we can take a look very quickly about how to apply them, right? Since these two rules are still very new in this week, let me just look at one of them, right? Implication R simply means we got the implication appearing to the right of the turnstile, which is this one over here. And that one there is really about shunting, right? So what we're going to do is we're going to move the antecedents over here to the hypothesis. That's what we got to do. Okay, let me just show to you. So this part over here is going to be moved to the left of the hypothesis. Sorry, to the left of the turnstile, or to the top of the turnstile. So it's now becoming the hypothesis. That's what we have by applying imp R. Right, so that's the only thing I would like to highlight to you, and the rest will be some quite standard. And let's take a look at this one over here. This one somehow cannot be discharged over here. Okay, let me just make it a little bit larger over here. We're going to analyze it together, but this one somehow just cannot be discharged. Right, if you look at that over here, given a plus b less than d, given c equal to 0, given MLTL equals green. Right, I'll talk about the meaning of that in just a moment in another page. We cannot really prove a plus 1 plus b less than d. So that's really where we got stuck. So the current model wouldn't really allow us to really discharge this sequence any further. So that's something we're going to do. Before we can find a solution, let's identify what the problem is. And you would run into a similar problem of unprovable sequence over here if you try the other events. Let me write it down for you, and that should be done as an exercise for you. Right, so you can try to do the exercise as follows. Try to specify and prove the following. IL out as opposed to ML out. And invariance 2, 4. And invariant preservation. This will be the exercise you can actually do. And when you do it, exercise over here, over there, you're going to see, you can expect it to see a similar unprovable sequence. It's a very important conclusion for you to confirm about doing the exercise over here, right? So what we'll do is we're going to focus on this particular sequence, but to really find the solution for this particular unprovable sequence, the solution will be very similar. We'll see. Okay, let's now take a look at this particular unprovable sequence and see what kind of hints it gave to us to really fix our model further. Let's first of all go back to the slides, and what we want to do now is to analyze the failed proof obligation over here, ML out, invariant 2-3 for preservation. And this is the failed sequence over here, and let's try to look at it more closely together on the iPad. Okay. Let's now switch to this page over here. And for now, just focus on this sequence over here and the diagram which I'm going to visualize about exactly what's being proved. And for this part here, I'm going to get there in a moment. Okay, for now, you can disregard it. Don't be distracted by this part over here. What we're doing is we are trying to prove ML out invariant 2-3, but somehow we got this unprovable sequence. That's where we came from. Let me highlight it. So we got ML out and also invariant 2-3. So let me highlight it. So it should be ML out over here and also invariant 2-3 over here. Let's see exactly what's being proved over here. The first one, A plus B, this is about ML out, right? So let me just try to visualize. We know that ML out is really about if a car can actually go out of the mainland, which is regulated by the traffic lights on the mainland side. ML out. Okay, let's look at the conditions over here. First of all, you can see MLT out should be green, so this should be a green light over here, and also A plus B less than D, meaning that the summation of A plus B over here should be strictly less than D because we're expecting one more car for ML out. So that should be A plus B strictly less than D. And also the opposite traffic from the other end over here should be equal to 0. Right? This part over here should be equal to 0. Given these conditions as the hypotheses, we want to prove the following. We want to say that assuming that this car is actually going to go onto the bridge, in that case, we're going to get A becoming A plus 1 based on the before after predicates over here. Right? You can see it's A becomes A plus 1. A plus 1 plus D less than D. Somehow this cannot be proved based on the hypotheses. Let me have you more focus over here. Given A plus B less than D, is it possible to prove A plus 1 plus B less than D? Is it general provable, or there might be some exceptions or counterexample? Even more generally, let's now talk about it. If I say x less than y, does that mean x plus 1 will still be less than y? This is is more like a simplified version of what we are trying to prove. Is this possible? Apparently this is not possible because, for example, what if, let's say x is actually equal to 3 and y is actually equal to 4. In this case, 3 strictly less than 4, true. However, 3 plus 1, 4. 4 strictly less than 4 itself is false. So we got true implies false. So this is unprovable. And let's now try to apply this understanding over here to our bridge controller. And let's now consider this fragment over here, which I told you to ignore before. But for now, let's now focus on this. And we're going to talk about different evaluation of the post-state version of the invariant number 3 over here after the occurrence of ML out, the post-state version. Right? So let me just be more precise over here. So we are talking about this. A plus B less than D. So that's specifically the constraint that could be problematic, right? So that's why we want to talk about here A plus 1 plus B less than D. The reason that it's actually A plus 1 is because we're talking about after the occurrence of ML out. Right? So that's something we knew from the context when we formulate the sequence, right? It's going to be the same for A plus 1 plus B less than D, right? The same. So I don't need to repeat the annotation. There will be some situation where the invariance can be preserved, in which case it will be evaluated true. There will be cases where the invariance will actually evaluate to false, meaning that it will be violated. In that case, we should really work out a solution so that the same invariance should still be preserved in this case. We'll talk about it in just a moment. But let's now get some idea over here. Let's say the maximum capacity between for A and B over here should be 3, meaning that the number of cars on the bridge and also on the island over here should be no more than 3, should be less than or equal to 3. And out of all the combinations of A and B over here, indeed we can subdivide it into 2 cases. Let's talk about the 2 cases, and then you will see how we can actually revise our model to really correspond to them. Case number 1 is about over here, and also we got case number 2, which will be over here. So what are the characteristics of each of the cases? Let's talk about it. For case number 1, given that we're gonna allow, let's say, the car which is waiting on the mainland over here, if we allow ML out to really happen, it's going to be A plus 1, right? There will be one more car on the bridge. So that's going to be A plus 1 and plus however many cars that are already on the island. That one there is not yet reaching the maximum. That'll be one case. Because if they have not yet reached the maximum, it should be allowed for another ML out to really occur, meaning that we should allow another car to really pass the green lights and then go onto the bridge. So this will be the case. Let me write it down over here. And in this case, that I'm really trying to explain the rationale about the design rather than throwing the solution to you. So this really tells you that another ML out allowed. What about the second case? The second case really is to say A plus 1 plus B. If we actually allowed the current car that's really waiting to follow through the green lights and go onto the bridge, in that case, we just reach the maximum, just equal to D. Meaning that after this has just happened, we should do 2 things. Number 1, we should really turn this light to be red. And number 2, consequently, that will disallow any further ML out to really occur. Alright, so we are really talking about 2 scenarios, and somehow these two scenarios are not really distinguished properly in a single ML out events. So that's why we might just want to split the ML out into 2 cases in terms of their guards. That's something I will talk about. But I think it's more important for you to understand the derivation process for the fixing. And let me write it down over here. When it is actually equal to D, so that means no more ML out should be allowed. And the way to do that is by turning this line over here to be red. ML, TL should be turned into red. It's very important for you to understand these two cases, right? Because in case number one, it would be okay to have the green lights to remain, the traffic lights, ML, TL, to remain green because we haven't reached the maximum just yet. And for the second case over here, in order to really preserve the invariance number 3 over here, we have to say what, because we have already just reached the maximum after the current occurrence of ML out. So we should really disallow another occurrence of ML out to really come, in which case it is actually going to falsify the invariance. But why setting this MLTL to be red will be useful? If MLTL is set to be red, in that case, MLTL equals green over here is going to become false, in which case false implies anything. So the invariant indeed can be preserved, right? It's also very important to see that. So once we set the MLTL to be green, to be red over here, let me just box it over here. So after this over here, this one can be can make sure the invariance 2, 3 is preserved, because once we set the MLTL to be red, MLTL to be green will be simply false. Implies doesn't matter. It will just be equivalent to true. False simply implies anything, right? So that's simply just provable automatically. It's very important for you to see this case as well, right? So understanding about these two cases, let's see how we can revise our ML events first of all, and then I will suggest how you can also revise about the exercise we assigned you to do before about the IL out, because you're gonna see some similar unprovable sequence. Let's talk about it. Okay, let's move on back to the slides, and then we'll talk about the fix. Right, so that's about what I just said on the iPad. You definitely can go over these cases again. The same case. We want to split into two cases over here. In one case, A plus B plus 1, the first case, we haven't yet reached the maximum, in which case we can still allow the ML to really occur, and also MLTL can remain to be green. That's okay. There's no danger of violating invariant condition number 3. On the other hand, if after the current ML occurrence we reach the maximum, that means no more cars should really be allowed to pass the green light from the mainland. In that case, no more later cars, and then we should really set the MLTL to be red, in which case we can falsify the antecedents of invariant 2, 3.